welcome to Alchemistry. So this video is about solid state chemistry, and here in this video I will discuss about chapter wise discussion, questions, point wise question discussion. As our chapter today is solid state chemistry, before going to the questions, let's go through the points quickly. The points that first see the reduced syllabus very well. After seeing the reduced syllabus, you have to go through the point. First point, the general idea about solids, that means amorphous solid and crystalline solid. After getting their property, few of the general properties, then we have the atoms, that position of atom, where the atom can be placed. That means the type of unit cell and Brevis lattice. Once we get that, we have a good idea about radius and edge length of the cube, that relation, and then packing fraction and vacancy fraction, that things. And from this part numericals may come, and then comes the density part. After density part, there are the defect part. Defect means that stoichiometric defect and non-stoichiometric defect. In stoichiometric defect, there is Fresnel defect and Schottky defect. Then we have in the non-stoichiometric part metal excess and metal deficiency defect, and then the paramagnetic diamagnetic compounds, and the copper, graphite, that structure, sodium chloride structures, that one. In the point wise question answer, I will go through the point and the questions regarding that, and here I am going to discuss the suggestive type of questions that may come from the particular topic. This video is going to be long. Be with me till the end. It will be helpful for you. So let's get started. Okay, so the very first thing we have crystalline solid. In crystalline solids, what are the property we can have in case of crystalline solid? We have, so the very first thing we have is crystalline solid. In crystalline solid, we have some property. In crystalline solid, the constituents are arranged in an orderly manner. They have definite geometry, flat face, sharp edges, etc. Such solids have sharp melting points also. They are considered as true solid, and they show anisotropy, and that is different physical properties in different directions. And the examples are like sodium chloride, potassium chloride, all the ionic compounds having crystalline solid. Then we have amorphous solid. In amorphous solid, constituent particles are not arranged. Such solid do not have sharp melting point. In amorphous solid, we have constituent particles are not arranged in a regular manner. They don't have sharp melting point. They are considered as pseudo solids, and they show isotropicity, and they don't show any cleavage. And the examples are rubber, plastic, glass, etc. Regarding that concept, let's see what questions may come. First question, which of the following is not a feature of solid? This one is direct type of question. So as we have seen the specimen copy, there are some direct question, indirect question. First direct question, which of the following will not be a feature of solid? Feature of solid, definite mass and volume. Feature of solid, rigidity. Feature of solid, definite shape is feature of solid. So the answer will be here frequent fluidity, which is not a feature of solid. So let's go for the next concept. Our next concept is placement of atom. What is that actually? This one is, so here in this case, as you know, we are considering basically the cubic lattice one. In cubic lattice, the atoms can be at corner. If atoms are corner, then what will be the contribution of corner atom? It is shared with other 8, so 1 by 8. If atoms are at the center of the face, then what will be the contribution of the atom? If it is at the center of the face, then contribution of each atom is half. If the atom is at the middle of the cube, then its contribution will be completely 1 to each for each atom. And if the atom is placed at the edge, whether it is middle or not, at the edge, it can be shared with other 4 lattices. Then the contribution will be 1 by 4. This general concept we need to have. Let's see regarding that concept what we have the question. Here in a face center cubic arrangement of P and Q atoms, atoms of P are at the corner. So we have the cube suppose. So atoms of P will be at the corner. Here the corner atoms are P atom. Here corner atom we have taken with a black ink. So these are the corner atoms. Q atoms will be at the center of the face. Now at the each center of the face, Q atom is there. Now one P atom is missing from one of the corners. So one of the corner, one P atom is missing. At first total number of corner was 8. Now total number of corner become total number of corner atom, number of atom P becomes 7. Now total number of P atom becomes P because from 8 corner, one of the corner, one atom is missing. Then the simplest formula would be, but Q is at the face. Now if we consider contribution of each corner atom is 1 by 8, total number of corner atom is 7. So total number of P for each cell will be 1 by 8 into 7. Now total number of faces are 6 and each atom will contribute half to the cell. So total number of Q will be 6 into 1 by half, 1 by 2. So Q is equal to 3 and P is equal to 7 by 8. Now the formula will be P 7 by 8 and Q 3. So ultimately we will get P 7 and Q 24. As you can see, P7 and Q24 will be the answer. Next, in the next question we have a compound formed by the element X and Y crystallizes in cubic structure. X atom are the corner. Again, a simple type of numerical we can get X atom at the corner. So we have total 8 number of corner. Total 8 number of corner. There will be total 8 atoms, 8 X atom, and the corners are occupied by the X atom. Okay, that are the X atom. And at the corner, Y atoms at the face center. So again the same type of thing, Y atoms will be at the center of the face. So here will be the Y atoms. Here will be the Y atoms at the center of the face. So once we got that, here no missing particles are there, so normal things will be calculated. If we take for X atom, contribution of for each of the X atom is 1 by 8. Total number of X, total number of corner is 8. So total number of X will be 1 and total number of Y atom will be each contributing half and total faces are 6. So 3. So the formula will be X and Y3. Option A will be the correct one for this question. Next question. Before going to the next question, we should have a knowledge about that. Simple lattice, total number of atom 1, body center 2, FCC 4, and simple the percentage occupied, percentage of the lattice, the cell occupied by atom is 52.4%, 68%, 74%. How to calculate the percentage of space occupied or the packing fraction, that you need to see my solid state video. Then we have radius and edge length relation. That means R is equal to A by 2 for simple, R is equal to root over 3 by 4 for BCC, and for FCC A by 2 root 2. Here is the relation between radius of each atom and the edge length A and radius of each atom. Next we go for the numericals regarding that concept. Next we have the percentage of empty space in a body centered cubic arrangement. So just now we had seen here the percentage occupied for body center is 68%. So what will be the empty space? Empty space will be 100 minus 68 will be the vacant part. So here answer will be 2 and 3. So 32%. Option C will be the correct option. Next, we can have a radius and edge length relative numericals. Sodium metal crystallizes as a body-centered cubic lattice with a cell edge 4.29 angstrom. So cell edge is given 4.29 angstrom. What is the radius? First thing, we need to know the radius and the edge length relationship. In case of body-centered cubic lattice, R is equals to root 3 by 4a. And another thing what we need to see, the unit. Here the unit is in angstrom. 1 angstrom is equals to 10 to the power minus 10 meter. That one is equal to 10 to the power minus 8 centimeter. So here the answer will be root 3 by 4 into 10 to the power minus 8 10 to the power minus 8 into 4.29 centimeter. After calculating it, we will get the answer. We will get the answer 1.857 into 10 to the power minus 8 centimeter. So option B will be the correct one. Next, we can have the numericals based upon the concept density. We have a definite formula of density. Let's see what numericals we have. A metal has a FCC lattice, that means Z is equal to 4. The edge length of the unit cell A is equal to 404 picometer. Now for picometer to meter, we have to multiply it by 10 to the power minus 12. So from meter to centimeter, we need to multiply it by 10 to the power 2. So becomes 10 to the power minus 10 centimeter. The density is given 2.72 gram per centimeter cube. First of all, in a numerical, you found out what the data are given, then what equation you know from the data. And Avogadro constant is given 6.022 into 10 to the power 23 mole inverse. Now we know the density having the formula total number of atoms Z into molecular mass of each atom, that is n by Na, divided by total volume of the cube. Total volume is A cube. To get the explicit knowledge, you have to see my solid state video. Next, what we have, Z, it is given 4 into molecular mass. Molecular mass is not given, which is required. We need to calculate the molecular mass here. So M we kept as M. Here Na is given 6.02 into 10 to the power 23 into A cube. We will put in centimeter, 404 into 10 to the power minus 10 centimeter. Why we are doing so? Because you see the density is given in centimeter cube. So 2.72 in 2.72 10 centimeter minus 3. So if we take on rho is equal to 2.72 gram per centimeter cube. That one is equals to m into 4 divided by A cube. That means here it is given 404 into 10 to the power minus 10 whole cube. That one is given in centimeter. So centimeter cube multiplied by 6.02 into 10 to the power 23 mole inverse. So if you go for the unit, you can see the unit will get cut out from there, centimeter cube and centimeter cube inverse from there, and gram remains and mole inverse remains. So from gram and mole inverse, if we calculate the m from there, taking this in the left side, so we will get m in gram per mole, 27 gram per mole. Always match the units also when you are doing numerical, then you can see whether your answer will be correct or not. So the answer will be here 27 gram per mole. Next we have the idea about the stoichiometry, non-stoichiometric effect. So then in this Schottky and Fresnel defect, we need to know the main things in Schottky defect. Cation anion goes out. When cation and anion equal numbers are going out, so density will decreases as volume is same here. As equal number is going out, so that means electrical neutrality will be maintained, as well as when that will be coordination number will be high, that will be the Schottky defect. In case of Schottky defects, we need to see some examples also, where another point, size of cation anion almost should be equal. Few points we need to remember, and Schottky defect and Fresnel defect is very important. Fresnel defect is where cation is going out from its side, lattice side, but it is taking interstitial side. And in which defect interstitial side is taking, that one is interstitial defect. In Fresnel defect, that density does not change. In Fresnel defect, the cation anion size should be varied, and it is possible for low coordination number. In non-stoichiometric defect, metal excess, metal deficiency. In metal excess, there can be cationic effect, anionic effect. In metal deficiency, also cationic, anionic effect. For more, go through my videos. Then what we have in Schottky defect, a lattice side is occupied by electron. This one is not true. The radius ratio r plus by r minus is low. This one is not also true. Some of lattice sides are vacant. Of course, this one is true. An ion occupies interstitial position between lattice points. That one is also not true for Schottky defect. So the only option correct, some lattice sides are vacant. That one is true for this, and an ion occupies interstitial portion. That one is not correct for Schottky defect. Next question we have assertion and reason type of question. As you have seen in the specimen paper, the assertion reason type of question is there. In any ionic solid with Schottky defect, the number of positive negative ions is the same. That one of course true, so assertion is true. Equal number of cation and anion vacancies are present, that one also true. So the answer will be A and R both are correct, and R is the correct explanation for A. Of course, equal number of cation and anion vacancy, that means equal number of positive negative ion is absent, so the correct option will be A. Then in the next question, graphite cannot be classified as conducting solid, network solid, covalent solid, ionic solid. Here for this one the answer will be ionic solid because graphite is conducting solid, network solid as well as covalent solid. So the answer will be conducting ionic solid. The next question we have, O2 is paramagnetic substance. This one is our assertion. Presence of unpaired electrons oriented randomly. So assertion is absolutely correct. So assertion is correct. So C can be true, A can be true and B can be true. Now presence of unpaired electrons oriented randomly. Because of presence of unpaired electrons, O2 is paramagnetic. So reason is also true and reason is the correct explanation. So option A will be the correct for that. So I have discussed the questions which are according to the specimen copy or which type of questions may come. Taking the topics and the conception also, follow this, study well and practice with me. I will publish more videos on chapter wise and point wise. So for this video, thank you for watching and keep watching. If you have not subscribed me yet, subscribe my channel, and if this video is helpful to you, please like it. Thank you.